Good morning, student. Let us start. We are discussing about scattering by ortho and parahydrogen. In previous class, we came up to this point. Scattering amplitude by neutron and proton is like this, where AS is the single scattering amplitude and AT is the triplet scattering amplitude. Sigma n and sigma p are Pauli spin matrices. We have calculated sigma n, sigma p to be 4 Sn dot of Sp to be 1 for triplet and equals to -3 for singlet, right? If you put this equals to 1 here, then A will be equals to 80 for this equals to 1 and A will be equals to AS for this equals to -3 as expected. So this is the scattering amplitude. Now for hydrogen atom, hydrogen molecule, there are two hydrogen atoms. So whenever we are performing an experiment with neutron on hydrogen, then there will be two scattering molecules, atoms, I say, sorry. So total amplitude A will be equals to A1 plus A2. Means there are two protons, either parallel or anti-parallel. One neutron is there, Sn, Sp1, Sp2. So A1 plus A2. So we have already derived the formula. So it will be 1 plus AS1 P8T1 plus 1 by 4 AT1 minus AS1 sigma n dot sigma 1, right? And the other will be AS2 plus 3 AT2 plus 1 by 4 AT2 minus AS2 sigma n dot of sigma P2. This will be like this. Now two are identical. Two hydrogen atoms in the hydrogen molecule are identical. So this will be this S1 and S2, T1 and T2 will be same. So this will be half AS plus 3AT plus 1 by 4 AT minus AS into sigma n dot of sigma P1 plus sigma P2. P1 plus P2. Now for hydrogen molecule, this is sigma P1 plus sigma P2. This can be written as, in the next line you can see that this sigma P1 plus sigma P2, I am not writing line again, sigma 1 plus sigma P1 plus sigma P2, this will be sigma H. So this is the expression. Sorry, sigma H. And now if you convert it with a spin, then this can be written as, so A will be equals to half S plus PAP plus sigma T minus sigma S into Sn dot of S, right? Because Sn dot of SH will be equals to 1 by 4th or 1 by 4th sigma n dot of sigma h will be equal to S. So this is our expression of total amplitude. Now what to find? We have to find differential scattering cross section. Now you can see that for paramolecule, this is equals to 0, SH equals to 0. So A will be equals to like this. And now for orthomolecule, S is equals to 1. So we have to calculate the average. Now for paramolecule, when S is equals to 0, we are left with for parahydrogen, SH equals to 0. Then we can write A equals to half AS plus CH. This is called coherent scattering length. Coherent scattering length. Now we have to calculate differential scattering cross section. Differential scattering cross section sigma equals to S. Right? So it will be equals to 1 by 4 AS plus CAT whole square plus AS plus CAT into AT minus AS Sn dot of SH plus AT minus AS whole square Sn dot of SH square. This is the problem. S plus 3 plus. Now incident neutron beam is unpolarized. If its polarization will be randomly oriented. So Sn will be equals to 0. Sn dot of SH will be equals to 0. Sn dot of SH will be equals to 0 because the incident neutron beam is unpolarized. So half of will be will be in up spin and half down spin. So this will be 0. Now Sn dot of SH square, take this average, and this will come out to be SH into SH plus 1, 4. Similar to the calculation we have made before. So sigma theta will be equals to now, we substitute this thing, then sigma theta will be sigma theta. Now sigma theta will be equals to S square to this. This is 0 and we are putting here this term SH. Now for ortho and paramolecule, we have to calculate this SH into SH plus 1. So sigma ortho will be equal to 1 by AS plus 380 whole square, and SH equals to 1. So this will be equals to 2. So it will be equals to 2 into 80 minus AS. So this will be 1 by 4. We work it out. Leave it. We don't have to simplify it. Do it later. And sigma para will be equals to, this will be equals to, SH will be equals to 0. So sigma para will be equals to simply 1 by 4 AS plus 380. Now, in the experiment in which orthomolecule and paramolecule are mixed, we cannot estimate the scattering cross section for sigma ortho and cross section for ortho and for para. However, molecules can be, hydrogen molecules can be made all to be para at a very low temperature of the order of 20 Kelvin. Then scattering cross section for paramolecules only can be found. Now, experimentally, it has been found that sigma ortho is greater than, much greater than sigma para. Experimentally, there is experimental evidence. Experimentally, sigma ortho is much greater than sigma para. So from where we can say that there is independence of NP force. Now let us calculate the ratio so that we can compare their strength of scattering amplitude, scattering cross section for sigma and ortho. If we take the ratio, then the ratio comes out to be sigma ortho by sigma para. It will be 1 plus 80 minus S square by 380 plus S. Now we have 80 equal to of the order of 55. You know 4.88. 4.8 fermion. We found it for Deutschland problem. And A is 23 point of the order of 24 fermion. They have found it for Deutschland experiment. Right? And if we put these values here, then this comes out to be, we have this value comes out to be sigma of 2 equals to 1.5 sorry, A is value plus and minus both, or A is equals to plus this will be equals to 21.8 for A is equals to minus 20. Right? Now we have already said the sigma ortho is much greater than sigma para. So we will take this one, not this. We will discard this one. Take this one. And this value is obtained for A is equals to minus 24. That means Fermi scattering length for singlet state is negative, which shows that singlet state for the empty system does not exist, because Fermi scattering length for a bound system or for a system to exist, its scattering length should be positive. Now, since we are getting sigma ortho and sigma para experimentally, the value is very large. And when we compare this thing with our theoretical consideration, we see that at once the scattering Fermi scattering length will be negative. This negative sign indicates that singlet state for which system? For NP system. NP system does not exist, or it will not be a bound state. Single state for NP system is not a bound state. That's why Deutsche problem we have seen that the spin were held. So we have completed the scattering, low energy scattering for NP system. Now we will move on to low energy scattering for PP system. Low energy PP scattering. PP scattering. Now PP scattering is very easier to perform because of the two reasons. One is the energy, monoenergetic proton beams can be obtained easily. And the other reason is that the energy of the incident proton can be varied. We can use accelerators, we can direct it by magnetic field, which cannot be done for neutron. The neutron is neutral, you cannot accelerate. But there are difficulties also. The difficulties are for the Coulomb interaction between the protons. For NP system, as neutron is electrically neutral, we don't have to consider Coulomb interaction. But in case of PP interaction or PP scattering, we have to consider Coulomb interaction. And the second point is, as NP, neutron and proton are two different particles, so the indistinguishability of two particles has not been considered. But in case of PP scattering, we have to consider the indistinguishability of two particles. So we cannot distinguish between two particles. Now, you know Rutherford scattering formula. Coulomb scattering. We can write if theta will be equals to eta twice k sine square theta by 2 exponential minus I eta ln where theta equals to E square by 4 pi epsilon 0 is cut. P is the velocity of the particle and K is mu E by equals to E will happen to square mu E by h. So this is the scattering amplitude. This is the amplitude. So cross section will be sigma coulomb. Direction will be h theta mod square. This will be equals to E square by 4 pi epsilon 0 m v square. A little bit of calculation and substitution. Find 1 by sin power to the 4 sin 2. You know this. This is Rutherford scattering formula. This is Rutherford scattering formula. Now we are performing scattering for proton beam. Protons. Now if you consider center of mass system, you know center of mass system, two particles are approaching each other. So in CM system, two particles are approaching each other. This is proton 1, this is proton 2. There is collision, so there will be scattering. So it will go like this. This plane will be, we are considering elastic scattering. So if plane of collision or plane of approach will be changed, say this angle is theta. Say this angle is theta. Now, if this is scattered by this angle, then the scattering angle will be equals to pi minus theta. But you cannot distinguish because if it goes there, if it goes there, then this photon will go there, right? First experiment detector. The first photon is going there to this detector. In the second case, this photon is going there. Second photon is going to the detector. Since both the protons are similar, therefore we have to consider scattering for angle theta and for the angle pi minus theta. So if you substitute, if you make theta equals to pi minus theta, and theta by 2 will be equals to pi by 2 minus theta. Therefore, the scattering cross section for pi minus theta would be, considering the indistinguishability of the particle, have to replace this formula, rather for scattering theta, it would be E square by 4 pi epsilon 0 mu E square whole square 1 by sin cot to the 4 theta by 2 plus 1 by cos cot to the 4 theta by 2. So now this is the formula. Now up to this the derivation is derivation is classical. But we have to consider quantum mechanical apply. You have to apply quantum mechanical treatment because since these are fermions, interchange of the particles will change its sign of the wave function. Therefore, we have to consider symmetrization of the wave function. Now, we see that to consider the symmetrization for proper symmetrization, considering proper symmetrization. we have f theta plus f phi minus theta. This is symmetry. On the other hand, f theta minus f phi minus theta, this will be anti-symmetry. Anti-symmetry. Now we know this is triplet state. T triplet is symmetry. This is symmetry. And singlet is anti-symmetry. 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 So to make the function anti-symmetry, we have to couple symmetric with anti-symmetric, symmetric with anti-symmetric, and this symmetric with this. So we have to couple these two forms. So scattering cross section considering quantum mechanical treatment. Quantum mechanical treatment says us that since these particles are fermions, protons are fermions, because spin is half, exchange of the particles, one is made, two and two is made, then its sign would be changed. Now for triplet state, if you change the particles, there is no change. You cannot distinguish between. But here, if you change the particle, the sign will change. So whenever we are considering scattering cross section, then for symmetric, this symmetric state, we have to couple anti-symmetric singlet state. And for this anti-symmetric state, we have to couple symmetric triplet state. So scattering cross section sigma c theta should be 1 by 4 theta plus f phi minus theta plus 3 by 4 f theta minus f phi minus theta. Now you know f theta and f phi minus theta. This is equals to, I am writing the first step to make you understand. Theta by 2 whole square exponential minus I theta ln sin square theta by 2 by sin square theta by 2 plus this thing exponential minus I theta ln this will be cos square theta by 2 by this will be cos square theta by 2 mod square plus 3 by 4 this thing exponential minus I theta ln sin square theta by 2 by sin square theta by 2 minus exponential I theta ln cos square theta by 2 by cos square theta by 2 I have taken 4 outside like this. Now, after simplifying this, we have to consider this to be A and this to be B. Then after a little bit of calculation, we find that the expression will be sigma c theta, that is the plus 1 by sin 4 to the 4 theta by 2 plus 1 by cos 4 to the 4 theta by 2 plus 2 cos ln cos theta ln tan square theta by 2 by sin square theta by 2 cos square. This is the first term. I'm extremely sorry. This will be like add up the two terms, then this will be like this. Eta by sigma theta, this will be equals to this thing into theta by 2k like this. Now, if eta is very small, this is small for proton of energy 1 MeV and higher. For proton of energy 1 MeV and higher, this term goes to this term tends to 1. So the expression for this expression is called, I'm sorry, this expression, right? More sigma, this will be equals to E square by 2 by epsilon 0 m this square 1 by n 4 theta by plus 1 by cos 4 theta by minus of theta ln tan square theta by 2 by so this is the expression for scattering cross section due to Coulomb index. This formula is called Mott formula. Mott formula. For we have eta equals to E square by 4 pi epsilon 0 h square b. Now for energy greater than 1 MeV, for energy E greater than 1 MeV for proton, this value of V will be larger and this ratio is very small. So this is very small. Value of eta is very small. Therefore, this term, cos term, this term will eventually become 1. So the formula will be like this. Now, if we compare this formula with the previous formula we have derived, when we have not considered quantum mechanical treatment, then you will see that for angle theta equals to 90 degree, this term is additional term. Now the effect of this term is that, for example, if you say theta equals to 90 degree, say theta equals to 90 degree, then theta by 2 will be equals to 45 degree. If you place this thing, then you see that this will be 1 by root 2 to the power 4 means 2 square 4 plus 4 8, but this will be again also 4. So 4 will be subtracted. So without this term, this would have been 8 times this, but with this term, this will be 4 times. So we can say that if we don't consider the quantum mechanical indistinguishability is not taken into account, then the sigma at an angle 90 degree is half or to the optic if we don't consider. And our experimental evidence, experimental observation is in agreement with the quantum mechanical treatment. That means for scattering of proton, you have to consider quantum mechanical. You have to consider it quantum mechanical. Now, up to this, we have only considered Coulomb interaction. Now we are going to take into account the effect of nuclear force. Now, for nuclear force, NP scattering, the expression for NP scattering has been derived. Now, since you know that nuclear force is charge independent, that means the force between two neutrons, between two protons, between neutron and proton are of the same nature. Therefore, we can use the formula for scattering amplitude for NP scattering for the proton. So when we consider the effect of nuclear force, this comes out to be amplitude g theta in the presence of nuclear as well as Coulomb force will be E square by 4 pi epsilon 0 mv square exponential minus I eta ln sin square theta by 2 this thing by sin square theta by 2. This is the expression for Coulomb scattering amplitude. And for nucleus, this term we have derived by 2k exponential 2I delta 0 minus 1. We have done for NP scattering. Where is this sigma 0 is the phase factor. This is the phase factor. Now, as in the previous case, we have to make the symmetrization and anti-symmetrization. Symmetric state will be g theta plus g pi minus theta, and anti-symmetric state will be equals to g theta minus g pi minus. So this has to couple, this is symmetry, this has to couple with singlet state, and this has to couple with triplet state. Right. So GS will be equals to CS theta will be equals to this thing will be equals to E square by 4 pi epsilon 0. We have just derived this formula 4 square exponential minus I eta ln sin square theta by 2 by sin square theta by 2 plus exponential minus I ln cos square theta by 2 by cos square theta by 2, that plus I by k exponential 2 I delta 0 minus 1. GS will be equal to this, and GA will be equal to this. We substitute this, and this will be equal to simply this term. Only this term will be there with a negative sign. So this will be e square by 4 pi epsilon 0 in this square exponential. Say I am in this minus IA by sin square theta by 2 minus exponential minus IB by cos square. Right? And this term will cancel out because there is a minus sign. Sure, you can see that for antisymmetric function, nuclear force does not contribute. Their nuclear force is present, but for this case, nuclear force is not contributing anything. So as in the previous case, scattering amplitude sigma theta will be equals to, you calculate it. Since you have calculated once, we will not go into detail. This is similarly sigma theta will be equal to 1 by 4 GS theta mod plus 3 by 4 GA theta mod square. This will be e square by 4 pi this whole square 1 by sin 24 theta by 2 plus 1 by cos 44 theta by 2 minus 1 by sin square theta by 2 cos square theta by 2. We have derived this expression just now, and for nuclear term this will be sin square delta 0 by k square. We have already done it for NP scattering. It will be same. There will be an additional term which is e square by 4 pi epsilon 0 mv square into sin delta 0 cos delta 0 by k sin square theta by 2. So we know this is Coulomb term. This is due to Coulomb term, and this is due to nuclear force, nuclear term. This term is the interference. So in case of PP scattering, three terms will be there. One is Coulomb term, given by Mott scattering formula. Another will be nuclear term, which we have derived is the same form as NP scattering. There will be another term, which is the interference between Coulomb interaction and nuclear interaction. Now, all these derivations are theoretical consideration. Now we will consider what is the experimental evidence behind this. Now, experimental result shows that PP scattering length is negative. So, if scattering length is negative, it can't be a bound state. So, PP system is an unbound state. And positive sign of delta 0 shows that pp nuclear potential is attractive. Delta 0 is positive, so it is attractive potential. We don't. So then experimental data, when inserted into theoretical calculations, then this gives potential for PP scattering. Q, PP scattering is somewhat smaller, 13.3 MeV, whereas it was 13 MeV for NP scattering. And the length, potential range B for PP was of the order of 2.58 per meter. We have taken it 2 for NP scattering. Now the effective range theory of PP scattering can also be done as we have done for NP scattering, and from which we can find the value of singlet scattering length and effective range of the singlet scattering, and which are found to be experimentally obtained value. Recently, experimental obtained value which we have given, I have already given in the note for NP scattering, which is AS is found to be minus 7.8, and if we add Coulomb interaction if is added, then this comes out to be minus 17%. And ROS of the order 2.83%. Now scattering cross section is plotted at different angles, and the figure will be something like this. This is the angle versus this sigma, differential scattering. It is symmetric, theta equals to 90 degrees. This flat portion, this is Mott formula. That means this is due to Coulomb interaction, and this term is for nuclear force. Nuclear interaction is this. Here it shows the interference between nuclear force and Coulomb. So that's all today. Next we will study the scattering, high energy scattering for NP and